So for stock price prediction, the time step information, if we consider the stock prices, it would be 1 week data, the current week data, and then we will have, this is the Tth week data, then we have the previous T minus 1 week data, then we have T minus 2 week data, meaning thereby this is, for example, 4th week of February, then 3rd week of Feb, then 2nd week of Feb. So this is your previous week data, and these are your time steps. So when we give the input to your RNN networks, we give the input as time steps, and your time step definition depends on your application or your research problem at hand, your input data. So time steps will go previous historical information, and then you need to give this time step information for your algorithm to learn. So here we talked about the concept of time steps. So I hope we are clear what are time steps in your RNN networks. Here we have defined U, V, and W matrices. So you will multiply whatever you are given as the input. If this is like the input at the time step, and we know that your input vector could have m number of features. So m is the number of features for univariate input. For one variable you have, for m variables you will have one input, and then your input will become a matrix. For example, this is feature 1, feature 2, feature 3, feature 4, and this is timestamp 1, timestamp t minus 1, t minus 2, t minus 3. Okay, let's redraw. We could redraw this in this format. You can also present this in this format. This is your time, for example, on the x-axis, and these are your features x. So x1, x2 up to xm. Okay, this looks much better now. So you're going to give the input at, for example, this is all your data, then these are your features that you are using to train your algorithm, and this is your time step. For example, this is your time step t, and we will give input t minus 1, t minus 2, t minus 3, t minus 4, and t minus 5. So we are going to give 6 time step information, and for example we will give input of the previous 3 time steps, so we will only include this information. For 3 time steps we will give input from all the features that we have, and only going 3 time steps. So this is 1, 2, 3, 4 time steps. Okay, so 4 time steps, previous data, current and previous data. We are going to give that input as xt, and collectively we call it x of t. So this is 1x of t, and how much time steps? We are taking 4 time steps. So we give the input and multiply it with your U matrix. So for each of these values there will be a value, and this will become the size of your U matrix, weight matrix, and then we multiply the previous hidden layer, intermediate hidden output, multiply with w, and then we have your f function, or we can say the f activation function. F will be your activation function, and once we have the output here, it will be again applying we will again apply an activation function g, to get your final output O of t. So g is the activation function for output layer, and f is the activation function for other layers, hidden layers, nodes. Okay, so the structure becomes like this: give your input, have an output, then again give your input, have the information from your previous time step, and add that to the sum part, and then activation function, and then your output. So this is how your information is going to go for different time step information for one input, one sample input, and you have these inputs x1 to x5. You're taking input from immediate, look at this, that this is important. You're taking input from the immediate, and this input from here is also has an effect of the previous time steps. This will include some impact of your previous hidden layer inputs. So x of t minus 1 are encoded into your ht of t minus 1, and ht minus 1 has information on the past. So here is an example of only one output, for example binary classification, and you have multiple inputs x1 to x5, and you are taking the input from only the previous hidden layer. So this layer only has input from this previous hidden layer, and so forth. Next comes these different type of models that I mentioned earlier. We have different models, types of processes. There's one input and you have many output. For example, image captioning, the input is an image and the output is a sequence of words. Many to one relationship, then we have in many to one relationship we could have sentiment classification. You give a sentence and the algorithm learns to predict or identify, interpret the sentiment in that sentence. Then we have many to many relationships or configuration model, such as your machine translation from sentence to sentence translations. And then we have saying many to many relationship. For example, this is current and previous 2 weeks data. Then we can use this to predict multi-step prediction. Step 1, step 2, step 3. This is current time t and previous information, previous time steps to predict t plus 1, t plus 2 and t plus 3. So you can do it. So for example, your existing model is like this, and then your model can use this information to predict. So this part will be the prediction, and this will be your historical information about your stock price. So from this point onwards, we don't have information about the future, and we will use the training of the algorithm to predict the future without the actual learning of your y values, or actual y values you don't have, and then you can use to predict the future. So we have multi-step prediction. You can predict multiple weeks output results, or you could also predict single step, like this example. You predict the next letter, so you give the input A, B, C, D. You give the input A, B, C, D, and only predict F. Every time you will give the input, next start from B, C, D, E, F, and then predict G. And then that becomes your input, and you predict the next step. So one-step prediction. This is one-step prediction, and the example that they have given in this model, in the example on slide 24, they have given multi-step prediction. So training for many-to-many, such as machine translation, we have an input x1 to xn, and we are trying to predict from yn to y1 to y, and we are trying to predict that. And what do we have here? Okay, something new on this slide. Look at here. What is this? This is your squared error. Here you have your squared error. Yi is the actual and O is the output. From this, O is the output. Actual output, we say here. And we have true value or ground truth. Usually we use this word ground truth. We have the ground truth and the, okay, just don't write actual output, just write output from the network, and we have the ground truth value yi. So okay, yi will be your ground truth and oi will be your output from the network. Okay, so why do we find the error? To update the model. This is required for updating the weight values. So all of them, the outputs will be used to update your error. And we know that we can update using the partial of error with respect to the weight values, or partial of error with respect to your bias values. So we update the weights using the partial. And for this step, we have partial of hidden layer I, and of course the hidden layer h of I requires your weight values. So h of I first with respect to weight, then we have error with respect to h of I. Then we have here an example they have given where this is the weight matrices on this part from the input to your hidden layer. And how do we calculate partial of E with partial of H? So partial of E, the next time step is also involved. So partial of E with respect to O, E with respect to O, then O with H, and then remember another component is your next value, E with respect to H of I plus 1, and H of I plus 1 with respect to H of I. So we are doing to update, we are taking the partials and we are trying to minimize the loss, and for that we need to estimate your partial or find the derivative, and then use that information to update your weights. Then we have the image captioning example where we have the input X. The X does not mean just one input. It could be a matrix like an image, 2D image. So we have X, and what about these parts? Because we have multiple outputs, right? Y1, Y2, In. So what about these? What can be the input? For this, we can use because this is supervised learning, we know the ground truth values or the actual values. We will use these and the input to train the network. Okay, so we can use them to train the network. And again, the process is the same. You have to find your error with respect to the weight values, and for that first we need to go to your HFI, and then from HFI you have to go and find your weight values partial with respect to weight values. And how do we find this part? This part is combination of two things: first next weight and the previous weight. Okay, HI plus 1 and H of I, 2 and 1, 3 and 2, 4 and 3, 5 and 4. This is the combination that they are talking about here. Then how do we do the testing? Again, so we can do is that we can give the output from here to the input for the next estimation of the next output. So we can give as input, and then we try to minimize the loss. Then we have feature input, and the output is a single value, for example binary classification. And again, the process is the same. You have to find the partials, and then for multi-input to multi-output, many to many, we know the model looks like this. You give the X, and then you can have your outputs. And this can be implemented. This is implemented using an encoder type model, where this becomes the input for the next model. And the beauty of this is that you only need this part, and then the input comes from here. Encoded input comes from the encoder side. So once this part is done at the testing, you can only give the encoded input, and it will generate the output. So this gives as given as an input to train the model, and then this is the encoder part, and this part. So for the test time, what do we give input over here? What we can do is we can give the actual inputs. This is combination of many to one and one to many. Many to one and one to many inputs. So one input and many output. It can also have that. And for that, we already know that we can use your YIs, the actual values, or your ground truth values. And for the test time, of course, your output from the previous layer can act as an input. So example of one to many is the image captioning, and your image can be represented by a convolutional neural network. And we do the word embedding at the input layer. When you give the input as a CNN, and then we have multi-step input, and it has a sequence model. Okay. And then machine translation, word embedding concept, I'm not including in this course, but of course if we extend to the course of deep learning, the word and embedding concepts and encoding concepts, they will be included. So for now I'm going to wind up the basic concepts of RNNs, and I hope that you're going to learn a little bit about RNNs, and if we were to implement or use them in some of our projects, these brief explanation could help you in understanding your algorithms better. So this is the end of today's lecture. If you have any questions or you have any queries, you can email me at this email address, or you could even comment on this lecture content at the channel. Thank you.